Now, let's talk about X-rays. And we all understand that X-rays play a vital role in predicting fractures in human bones or animal bones. And these X-rays are basically electromagnetic radiations. So let's talk about the production of these X-rays. And these X-rays could be produced in a tube known as Coolidge Coolidge X-ray tube. Now, what this Coolidge X-ray tube is that we have some filament, and for this filament we have to have some external supply, and then from this filament what we do is we produce what we call as electrons using thermionic emission. And then we have a plate. We draw a plate, a target plate, and we go like this. And this setup is enclosed. This setup is enclosed in a tube. Let me go with the tube kind of thing, and then we have some cooling atmosphere for the system, and where we introduce the coolant, and this coolant is exhausted out. And what we have from here is thermionic emission, the electrons, and we can have what we have as X-rays. So to say about this Coolidge tube is that when the pressure of this tube is of the order of 10 to the power of minus 13 mm of Hg, and we have an electric discharge, and this electric discharge is passed between the cathode and anode, and the glass walls of the discharge tube behind this cathode. What happened in original experiment? What happened in the original experiment is that a yellowish glow was observed. Now, after performing a series of experiments, it was Rontgen basically. It was Rontgen. He concluded that highly penetrating radiations of unknown nature are produced when a beam of fast-moving electrons strike a solid target as tungsten. So here we have a tungsten target. Now the production of these X-rays, and they were called as X-rays because things were not clear about these kind of rays, what these rays actually are. So these X-rays are produced by bombarding this solid target with these fast-moving electrons. And this whole setup is a schematic way of talking about a Coolidge X-ray tube. And what happens is that this filament that we have, it is heated by virtue of, and we have to have some supply for the tube, and this supply has to be very, very large, of the order of 100,000 volts. So let me have, okay, this is the situation. Okay, so what we are doing is that we are allowing the current to pass through this filament using this low tension battery, and at the same time about 100,000 volt of voltage is applied between this cylinder surrounding the filament and the target. And the electrons that are emitted by the filament, they are accelerated by this high potential difference and between the cylinder and the anode that we have. So the stream of highly energetic electrons that are focused on this target, when these energetic electrons fall on this target, most of the energy of these electrons is converted into the heat energy. And only a fraction of energy of the electrons is used to produce the X-rays. And this is why we have the coolant, so that the temperature that will rise in the system can be moderated using this cooling system. Now, this is how X-rays are formed, and these X-rays have some important properties. These X-rays, first of all, they are electromagnetic waves. They have very short wavelength, and their wavelength ranges between 0.001 nanometer to 1 nanometer. They are highly penetrating rays and can even pass through the solids, which are opaque to the ordinary light that we have. They can affect, these X-rays. They can affect the photographic plate more effectively than the ordinary light, and they have a destructive effect on the living tissues. Because they are a radiation that they can interact with the atoms of the tissues, and they can cause destructive damages to the tissues. And what they does is they ionize the gas through which they pass. So when you have a gas, they allow them to pass through the gas, and the atoms of that gas can be ionized using X-rays. And they eject electrons from certain metals. When you bombard these X-rays on some metals, they fall. They can eject, if this is a metal, for the sake of argument, can eject the electrons. So you can cause photoelectric effect using X-rays, and they travel with the speed of light. They have the speed same as that of light. That's 3 × 10⁸ meter per second approximately. And they can be diffracted. I mean, they will show you the wave nature, and they can also be polarized. So they have everything that light has, apart from very, very small wavelength and highly energetic radiation. Now, this X-ray spectra that we have, I mean, there are two types of X-rays, and one is called as continuous X-rays, another one is called as characteristic X-rays. So to talk about this continuous X-rays, if I plot a graph between the wavelength in angstroms and the intensity, and what am I able to observe is something like this. Performing the same experiment, something like this, okay, and something like this, and so this is for 25 kV kilovolts. Then this is for 30. I have missed the peak basically, kV and 40 kV. Okay, so this continuous spectrum that we have here, it consists of all the wavelengths larger than a certain minimum wavelength that we have, lambda min, lambda min, lambda min. And this spectrum is independent of the nature of the material. It does not depend on the nature of the material that we have used, and varies with the applied voltage across the target and the cathode of the X-ray too. Now, the distribution of the intensity that we have here with the wavelength for different accelerating voltages, we can see that for more accelerating voltages, we have more intensity of X-rays that are coming out. And what is most important here is that what we observe is that we have a minimum wavelength limit, and that is lambda min. And this limit decreases with increasing voltage. So we can see here that as we have increased the voltage for this graph, we have this voltage for this graph. Then as we increase the accelerating voltage, this lambda min is decreasing. It's going towards the left of the axis. And then we can say from this, what we can conclude is that this lambda min the minimum wavelength, it must be proportional to the accelerating voltage. So as you increase the accelerating voltage for particular measurement, the lambda min for that is going to decrease. Now, what could be the possible mechanism of this what we call as characteristic X-rays continuous X-rays. So what we have is these continuous X-rays. They are produced by a phenomenon known as Bremsstrahlung. Bremsstrahlung. And I probably believe it's a German word, and it means breaking radiation. It means breaking radiation. Now, when electrons are emitted from the filament that I have shown you in the College tube, when the electrons are emitted in the College tube, and what we see is that they are accelerated to the target. We have the target, and electrons are accelerated towards this target, and they penetrate deep into this target of the atoms of target material and are attracted by the nucleuses of the atoms that this target has. Okay, so if I come up here, so we have a nucleus and we have an atom, say for example. So what happens here is that when these radiations go deep into these into the target material, what happens is that the nuclei of these atoms, they exert some strong electrostatic interaction with the electrons that are moving in vicinity of these nucleuses. Therefore, electron deviates from its original trajectory. So what's happening? The electron is going, and it deviates. So deviating from its original path and getting decelerated. So there is a deceleration going on, and the velocity and hence the kinetic energy of the electron decreases. So there is decrease in the kinetic energy of this electron. So electron coming, moving in vicinity of nucleus, having a strong electrostatic interaction, losing the energy. This loss of energy that we have, this loss of energy during this retardation that we talked about here, deceleration, retardation, it appears in the form of electromagnetic radiation, and that is X-rays. And what we call them X-rays of continuously varying wavelength. So the X-rays that will be produced by this phenomenon will have a range of lambdas in it. That's why we call it continuous spectrum of the X-rays. Now, these X-rays consist of continuous range of frequencies, ranging from some maximum frequency, say for example V max, or at the same time some minimum wavelength, lambda min. Okay, and this lambda min is called this lambda min. This is called this lambda min, that you have the range of frequencies that I talked about here in this graph that we have. This is called as continuous X-ray spectrum. Now, let us assume that the velocity with which an electron moves, or the change in velocity of an electron from nu1 to nu2 due to the electrostatic interaction. So this energy, the energy of the emitted photon, due to the retardation of the velocity of electron, so we have to have V1 and V2 here. That energy that we will have will be simply 1/2 of m V1 square minus 1/2 of m V2 square. So the change in kinetic energy of the electron gives rise to the electromagnetic radiations. Now, when the electron is completely brought to rest, suppose we think of electron momentarily completely coming to rest by the electrostatic interaction. Now, in that case, the entire kinetic energy of the electron is transformed into the photon energy. That's what we will say here, that the photon has emitted a maximum frequency or the minimum wavelength. Now, what is important for that is that when it comes at rest, it means V2 is equal to 0. So all of the energy that comes out is basically the kinetic energy of this electron. And if we assume that we have applied a potential difference between the cathode and the target to accelerate this electron, then we can say that this 1/2 of mv1 square is simply equal to ev, where E is the charge of the electron and V is the potential difference that has been applied. Now, what we can see here that this EV is equal to h nu max. This is max now. This is maximum frequency. That means minimum wavelength. So here for nu we can use c by lambda, and what we will have is EV is h c by lambda min. So this lambda min that we talked about, this lambda min is inversely proportional to the potential difference across the Coolidge tube. Now, this equation, this equation that we have, it's also called as Duon. It's also called as law of Duon and Hunt. Okay, so which states that the minimum wavelength lambda min called the continuous spectrum limit, which is the limit of this continuous spectrum that I have shown you in the beginning, is inversely proportional to the applied voltage. And if we talk about the frequency nu max, it is directly proportional to the applied voltage. So this is what continuous X-ray spectrum is all about. Now talking about characteristic X-rays. Characteristic X-rays. Now, in addition of these continuous spectrum obtained from the target, we can have some sharp lines, and that appear at sufficiently high voltages, and these lines that we obtain, they seem to have some imposed on the continuous spectrum. Now these sharp lines are due to X-rays of some definite wavelength, and if we take on this as lambda min, so when we have some extremely high voltage that we apply, we appear to have a peak, then it goes down, and then we appear to have another peak, and then it goes down. So if this is my lambda, so this should be my lambda min that was defined in the continuous X-rays, and this is intensity in some arbitrary units. So what is happening here is that we have some sharp lines observable in the X-ray spectrum, and they correspond to some definite wavelength. These peaks correspond to some definite wavelength, and they certainly depend on the nature of the material. Nature of material. In the previous case, in case of continuous X-rays, they don't depend on that spectrum does not depend on the nature of the material. But here what we see experimentally is that they depend on the nature of the materials. Hence, these X-rays are known as characteristic X-rays, and the characteristic X-ray spectrum of an arbitrary element that I have chosen here to explain the curve, the intensity variation curve. Now, in order to explain this phenomenon, what happens is that when electrons accelerate through some potential or allowed to fall on the atoms of a target, the electrons of the atoms of target are basically knocked out. So if I have an atom, it has a nucleus, then it has the orbits. And what happens now if we have the electrons bombarding on the material, and what happens in certain cases is that the inner orbit, now if this electron, suppose this is an inner orbit electron, if the electron from the inner orbit is ejected, which we call as K shell, if this is knocked out, then the vacancy created by this knocked electron can be filled by the electron from some higher energy level. okay, and from some higher energy shell of the atom. Now, if this vacancy is filled by an electron from second orbit, in our case, which we call as L shell, then X-rays are X-rays are emitted in the form of a photon, giving rise to some special line of frequency, and the frequency of that line will be simply EL minus EK by H. That should be the case. And this spectral line appearing in the specimen, in the spectrum that we have here between the intensity and wavelength, this shall be called as K alpha line. Now this is K alpha line. Okay. Now if the electron in the innermost shell is filled by an electron from the M orbit. Suppose I take into account another M orbit, an electron is ejected first. Now we have an electron coming from M orbit. Now it emits the radiation. So then the X-rays that are emitted in the form of a photon that give rise to spectral line of frequency defined by EM. It should be EM minus EK by H. Now this spectral line is called as K beta line. Okay, so this is how the characteristic X-rays are produced, and these characteristic X-rays are purely dependent on the nature of the target material. And characteristic in case of characteristic X-rays, what happens is that we have the electrons that are coming from the filament, they hit the target and they knock out the electrons from the inner orbits. And when these inner orbits are filled by the outer electrons, in order to gain the minimum energy, the energy is emitted in the form of some peaks. In this example, what we talked about, K alpha line and K beta line. Now, K alpha line is for a transition from L to K, or a transition from M to K will refer to K beta line. So this is how we demonstrate the characteristic X-rays. So what we have tried to understand in this video is what are X-rays, how these X-rays are produced, and what are the important properties of these X-rays, and what are the two important kinds of X-rays, and one is continuous X-ray spectrum, and another is characteristic X-ray spectrum. And we have tried to understand these important things linked with X-rays. Bye.